So we'll just start by reminding ourselves about number systems. So we have natural numbers, the notation is capital N, and natural numbers are the set of whole positive numbers, okay, like 1, 2, 3, 4, 5 onwards. Integers then, which have the notation capital Z, are the set of all positive and negative whole numbers. So minus 3, minus 2, minus 1, 0 is in there as well actually, and 1, 2 and 3 are considered to be integers. And then we have rational numbers, or otherwise known as fractions. So rational numbers are any numbers that can be expressed, such as A is divided by B, and where A and B are from the set of integers, i.e. they're positive or negative whole numbers. So 10 over 1, 1 over 2, minus 2 over 3 are all examples of rational numbers. Okay, numbers which can be expressed in fractional form. Okay, and just to say that natural numbers are a subset of integers, and we see here in the Venn diagram, and integers are a subset of rational numbers. And we can use any of these natural numbers, integers or rational numbers, to solve equations like this one. X plus 5 equals 3. That means that x equals 3 minus 5. X is equal to minus 2. So x is equal to minus 2, and just to remind ourselves that 2 is from the set of integers. Minus 2 is an integer. Sometimes we might be asked to solve an equation like x squared is equal to 2, and we know to find the answer for the value for x, then we get the square root of both sides. The square root of x squared is x, and that's equal to the square root of 2. But it's actually plus, or the square root of 2 plus or minus that answer, because a minus by a minus number will give a positive value anyway. Okay. Now, if we were to type root 2 into our calculator, we'd see that the answer we would get would be a non-repeating, non-terminating decimal. In other words, it never stops and it never repeats. Okay, and if we consider this, we'll realize that in fact root 2, or the value of root 2, this non-repeating, non-terminating decimal, it can't actually be written as a fraction. Okay, and this means therefore that root 2 is considered to be, or is known as, an irrational number, as is the square root of 3, the square root of 5, because they can't be written as a fraction. They will always give non-repeating, non-terminating decimals. Pi is the most famous irrational number. Okay, the value of pi is 3.14, blah blah blah, and it can't be written as a fraction. And sometimes in maths, you have seen in the past that it's approximated sometimes to be equal to 22 out of 7 to solve particular problems, which is funny or interesting, given that pi is an irrational number which can't be expressed as a fraction. But actually, if you remember or cast your mind back, pi is actually, for any given circle, the ratio of its circumference over its diameter. And so relating going back to our number systems then, we see that natural numbers are a subset of integers, which are a subset of rational numbers, which are a subset of irrational numbers. Which gives us, which are all a subset of real numbers. Okay, so real numbers are basically all numbers, positive, negative, repeating, non-terminating, decimal. Every number that exists is a real number. So let's show that 5.2 is a rational number, i.e. can be expressed as a fraction. Okay, so if we rewrite 5.2 as 5 plus 2 tenths, and that's equal to 5 plus 1/5, and 5 5s are 25, and 1 is 26 over 5. 5.2 expressed as a fraction is 26 over 5. That proves that 5.2 is actually a rational number. It can be expressed, it's decimal, but it can be expressed as a fraction. And actually, when we look at 5.2, we see that it actually terminates And actually, if we take another example then to express or to prove that 0.333, which terminates and is recurring, the 333 is recurring, let's see if we can write that or can be written as a rational number. Okay, so the proof of, or the answer is, if x is equal to 0.333, then 10 times x is 3.33, and x itself is 0.33. If we take one from the other, we have 10 minus x is 9x is equal to 3. So that means that x is equal to 3 over 9. Here, that should be 3 over 9, which is the same as 1 over 9, 1/9. 0.333 is equal to 1/9. It can be written, or sorry, as a fraction, it proves that 0.333, which terminates and is recurring, is a rational number. And here's the final one then. Let's show that the square root, the number, which is the square root of 16 over 9. Let's prove that that number is a rational number. Well, that's the square root of 16 over 9. Square root of 16 is 4 over 9. That's a rational number. We've written it as a fraction. We've simply just reduced, we've got the square root of the root 16, found that to be 4, and we just leave the 9 as is. It's a rational number. So the fact that we have a square root sign in the number doesn't necessarily mean that it is an irrational number. It can still work out to be a rational number. So let's consider complex numbers now. Let's move on to complex numbers, and if we think about it, if we just start by saying that the square root of 25, that's equal to 5, and we can prove that to ourselves because we can say 5 times 5 is 25. And the square root of 36 is 6, 6 is the 36. Square root of 100 is 10, 10 times 10 is 100. But what about the square root of a negative number like minus 4? It's not 2. The square root of minus 4 is not 2, because 2 times 2 is plus 4. And the square root of minus 4 is not minus 2 either, because minus 2 times minus 2 is actually plus 4 as well. So we say that this square root of minus 4, it's not actually a real number, as we mentioned real numbers in the last slide. It's what's known as an imaginary number. Okay, and in complex numbers and in maths, we use the letter I, small I, to represent the natural number that is equal to the square root of minus 1. And we further go on to say that if we were to multiply the square root of minus 1 by the square root of minus 1, in other words, I squared, then that's equal to minus 1. Okay? And moving on from this then, we can then work out what the square root of the negative number that is minus 9. Well, square root of minus 9. Square root of minus 9 is the same as the square root of 9 times the square root of minus 1. Okay, it's the product of 9 by minus 1 is minus 9, so we can rewrite it like this under the two square root signs. And that's the same as the square root of 9 by I, because remember we said that the square root of, or we're going to start using the fact that the square root of minus 1 is equal to I. The square root of 9 is 3, so actually our answer is 3i, and this 3 here is the imaginary number. Okay, the square root of minus 25 can be rewritten as the square root of 25 times the square root of minus 1, which can be written as the square root of 25 by I, because I is equal to the square root of minus 1. Okay, and the square root of 25 is actually 5, so it's 5i, and the 5 here is our imaginary number. And going back here to our minus root of minus 4, what's that equal to? Well, that can be written as the root of 4 by the root of minus 1, which is the root of 4 by I, which is equal to 2i. The square root of minus 4 is equal to 2i. And so in maths, we can write numbers in their real and imaginary parts. So we can come across a number which has a real part 3 plus an imaginary part 4. And if we were to write that, we always write complex numbers in the form a plus bi. So that's the real part is here and the imaginary part is the coefficient of I. And so, keeping with the notation, the number 5 can be written as 5 plus 0i. That's its real part and its imaginary part. The number minus 6i can be written as 0 for the real part, because there is no real part, minus 6i with its imaginary part there. Okay, and we use capital C to notate the set of complex numbers, and we generally use a lowercase z that's used to represent a complex number, i.e. z subscript 1 or z1 is the complex number 2 plus 3i if we were doing an example. Okay, so what kind of problems do we meet with in this chapter? Well, we might be asked to simplify the root of minus 4. We might find what is the minus 4, square root of minus 4 equal to, and we just did that one actually earlier. That's the same as root 4 times square root of minus 1, same as root 4 by I, which is 2i. Or we might be asked to write the real and imaginary parts of the number, the complex number, minus 1 plus 9i. Well, the real part is minus 1, and the imaginary part is the plus 9. If we take this example here, this number, x minus 2 plus 6i, well, from this complex number here, this is the real part, x minus 2, and 6 is the imaginary part. Okay. How about this one here then? Write in the form a plus bi the number 6 plus the square root of minus 16. Well, that's the same as 6 plus the square root of 16 times the square root of minus 1, which is I. So that's 6 plus square root of 16i, and simplifying that further, that 6 plus the square root of 16 is 4i. This is the real part, this is the imaginary part. 6 plus 4i is the complex number that originally was 6 plus the square root of minus 16. So let's look and see how we can add and subtract complex numbers. So let's add 3 plus 2i to 4 minus 3i. Well, basically to add or subtract complex numbers, we simply gather the like terms, we break out the brackets, so we have 3 plus 4 plus 2i minus 3i. 3 plus 4 is 7, and 2i minus 3i is minus 1i. Let's have a go at this one here. A plus bi plus c plus di. Well, if we break out the brackets, we have a plus bi plus c plus di, just by simply removing the brackets. We gather the like terms, the non-I terms here, or sorry, the real parts, a plus c, and we gather the imaginary numbers b and d because they're the coefficients of the I, and a plus c, we'll just neatly put that in the brackets there, plus b plus d all times I. This is the real part of the answer, this is the imaginary part of the answer. In the next video we'll go on to looking at multiplying a complex number by a real number.